Hi, hello. Welcome to my channel, Dr. V.R.K. Reddy. In this video lecture, I will be covering second order linear homogeneous differential equations with constant coefficients. In the last video, I have discussed general cases with a general equation. Now, in this lecture video, I will be covering all those three cases with examples. So, the first one is that let's start with first example. Now, we have seen that how do you approach this solution. We have seen this in the previous lecture video, so where we have taken the any arbitrary constant. In that case, we have assumed let y is equal to e power mx be the solution, hence y prime is equal to m e power mx and y double prime is equal to m square e power mx. Now, there is a double derivative term, there is a single derivative term, and there is a constant without derivative term. Now, you substitute all these values. After substitution, you will be getting m square e power mx and minus 6 times m e power mx plus 8 e power mx is equal to 0. If you take e power mx common, m square minus 6m plus 8 is equal to 0. Anyway, we know that e power mx cannot be 0, otherwise you are getting a trivial solution. So, to get a non-trivial solution, this must be non-zero for non-trivial solutions. That is non-zero solutions. Hence, that implies m square minus 6m plus 8 is equal to 0. Therefore, m is equal to minus of minus 6 plus or minus square root of minus 6 whole square minus 4 into 1 into 8 divided by 2 times 1. That is, you are getting actually 6 plus or minus this is 4 divided by 2, that is 6 plus or minus 2 divided by 2, that is 3 plus or minus 1, which is equal to 4 comma 2. These are the roots. Of course, you can get it similarly here, m square minus 4m minus 2m plus 8 is equal to 0. Here the product of the roots is 8 and then sum is minus 6, it is satisfied. Therefore, m square if you take common and m minus 4 is equal to 0. If that is m minus 4 times m minus 2 is equal to 0. That implies m is equal to 4 comma 2. Same result you can get in different way also. Now, if these are your roots, therefore these two roots are distinct. We have a second order ODE with constant coefficients . Why it is constant coefficients? All those coefficients involved here, and this is minus 6, this is 8, those are constants. Therefore, this is a differential equation with constant coefficients. Since there is no there are no non-zero terms other than terms with y. That means everywhere you see there is a dependent term. There is no term at all, non-zero term in the differential equation with without y, non-zero term. No such terms are there. Therefore, you are calling this equation is homogeneous equation because of this, and homogeneous equation. So, every term you take, everywhere y is there. So, other than y, there is no term. Without y, there is no term except 0. Therefore, we call it is a homogeneous equation. And you should have, it is a second order differential equation. You should have two roots. The two roots are, therefore, roots are 4 comma 2. So, these are distinct actually. Distinct real root. Distinct real roots. Therefore, your solution, that is the complementary solution YC or YH, Y homogeneous, whatever it is, or Y general solution, since the given equation is simple homogeneous equation, you can write it C1 e power m1x first root plus C2 e power m2x, that is the second root. That implies y is equal to c1 e power m1 is 4x plus c2 e power 2x. If you want, you can write further, or c1 e power 2x plus c2 e power 4x, both are same, both are same. So these c1 c2 are dummy arbitrary constants, and we call it, this is general solution, general solution, because if you want to fix c1 and c2, we should have the initial conditions or boundary conditions, because this is a second order differential equation. You should have two boundary value or initial value problems to solve this, to fix this c1 and c2. This is the general solution. C1 and by varying C1 and C2, you will be getting many curves. All those curves are solutions to the given, and all those curves are solution to the given differential equations. Now we will take a differential equation where repeated roots are possible. Whenever repeated roots are there, how do you get the solution? Suppose example 2, find the general solution of y double prime minus 8y prime plus 16y is equal to 0. This equation also, every term is having y, every non-zero term is having y everywhere. Therefore, this 1 and then minus 8, 16 are constant coefficients, constant, those are fixed constants. And on the right hand side, this is 0, and that means there are no terms without y, there are no non-zero terms without y. So whatever the terms are there, these are with y only. Hence it is homogeneous equation, and you are actually solution, let y is equal to e power mx and y prime is equal to m e power mx and y double prime is equal to m square e power mx, and we have covered all those derivatives present in the given differential equation. Therefore, you can substitute all those things. M square e power mx minus 8 m e power mx plus 16 e power mx is equal to 0. E power mx, again it is m square minus 8m plus 16 is equal to 0. This is m minus 4 whole square is equal to 0. For non-trivial solution, I should mention that solution e power mx is non-zero. Therefore, you have m is equal to 4 comma 4. When you write the general solution, y is equal to c1 e power 4x plus c2 e power 4x. You can look at it, you can simplify further, c2 e power 4x. Therefore, this is a new constant, a e power 4x. What about the second solution? Second solution, since it is a second order differential equation, since the given ODE is a second order ODE, we must have two linearly independent solutions. So whether you have or not, you have to check it. Now you can see that you are only having one solution. What about the second solution? Second solution is what? So to get the second solution, we are actually choosing the second solution is of the form just y2 is equal to x times e power 4x, x times e power 4x. E power 4x was the earlier solution, y1 is equal to e power 4x. To write the second solution, y2 is equal to e power 4x, then you realize that these two are not alike, not linearly independent. To get that linearly independent, you have shaped in this way. Of course, you can imagine this is multiplied with y1 also multiplied with x power 0 e power 4x. Whenever there is no repetition, it is 0 degree term. Whenever there is a repetition, it is first degree is appearing. Suppose, therefore, y general solution is c1 e power 4x plus c2 x e power 4x, that is c1 plus c2 x e power 4x. That is your solution. Now you have two linearly independent solutions. First solution is e power 4x. Second solution is e power 4x. These two are Li. You can check it by writing e power 4x, x e power 4x, and derivative of e power 4x and x e power 4x derivative, and apply determinant. You should get non-zero. Then you can say that these two solutions are linearly independent. Now suppose if we have three same roots like 1 comma 1 comma 1 for a certain differential equation, certain third degree third order ODE, then what is your solution? Then the solution will be of the form y is equal to c1 e power x plus c2 x e power x, because m is 1 here, in this case m is 1, and plus c2 c3 x square e power x. If you take e power x common, that is the root. Now you have c1 plus c2 x plus c3 x square. You see here, since it is a third order, if there is any third order differential equation is there, you should have three constants, arbitrary constants, c1, c2, c3. But of course, it starts with something you can imagine, x power 0, x power 1, x power 2. This is third order differential equation, therefore less than the third order, because you are starting from x power 0. This is how you are writing. This is true even for any. Now example 3, where we have complex roots. So now we have seen in the first case real roots, and the second case is also real roots, but repeated roots are there. In the third case, we are handling purely complex roots. So before I take you, please recall this: cos e power ix is cos x plus I sin x, and of course similarly e power minus ix is equal to cos x minus I sin x. Further, you have cos x is equal to e power ix plus e power minus ix by 2a. Similarly, sin x is equal to e power ix minus e power minus ix by 2i. These formulas you should note it down, and then we can solve the problems, ODE problems, where the complex roots are possible. Suppose example 3, right? Find the solution to the differential equation d square y by dx square minus 16 in 6 into y d square y by dx square minus 6y prime plus 13y is equal to 0. Now if you take it, y is equal to e power mx and y prime is equal to m into e power mx, and y double prime is equal to m square e power mx, and substitute all those things, leads to m square minus 6m plus 13 into e power mx is equal to 0. But e power mx is non-zero for non-trivial solution. Therefore, we have m is equal to minus of minus 6 plus or minus square root of minus 6 whole square minus 4 into 1 into 13 divided by 2 into 1, which is equal to minus into minus is plus or minus square root of 36 minus 6 plus or minus square root of 32 minus 52 divided by 2, which is equal to 6 plus or minus 4i actually, because minus 16 you can see this is I square times 16, therefore this is giving divided by 2. This is equal to 3 plus or minus 2i, m is equal to, therefore if you want to take m1 is equal to 3 plus 2i, m2 is equal to 3 minus 2i. If you write this solution, that is c1 e power m1x plus c2 e power m2x, which is equal to c1 e power 3 plus 2i into x plus c2 e power 3 minus 2i into x. If you simplify, c1 e power 3x e power 2ix plus c2 e power 3x e power minus 2ix. Now, if you take e power 3x common, that is c1 e power 2ix plus c2 e power minus 2ix. Further simplification leads to c1 into cos 2xi, sorry, cos 2x plus yeah. Further, if you simplify, this is equal to e power 3x into c1 cos 2x plus I sin 2x. Similarly, you have c2 times cos 2x minus I sin 2x. Now, if you combine e power 3x times c1 plus c2 times cos 2x plus I times c1 minus c2 sin 2x. So, these are some constants. Therefore, let it be A. This is let it be B. Therefore, e power 3x into a cos 2x plus b sin 2x. So, that is your general solution whenever there is a complex root. What are the possibilities when m is equal to, when you see that in this case, specific case, when plus or minus ib is there. So, if a, that is, this implies e power a plus ib into x, e power ax, e power ibx. Suppose no real root, no real part. In that case, a is 0. Therefore, your solution is m is equal to, roots are this one, and your solution is e power ibx plus or minus, of course you have, and you have to write it, which is equal to cos bx plus or minus I into sin bx. So, this is how you are writing. Whenever no real part, you can easily simplify further. So, this is how you are solving these problems whenever there are roots of real, distinct, real repeated, and real complex roots. This case is real repeated, real distinct roots. This is real but same roots, real but same root. That is called repetition. There is a repetition. It is repeating twice in this case. And you have the third case is like complex roots case. So, if anybody wants to extend this problem, suppose they can give the initial values or boundary values. For example, initial value problems are defined at a specific value in the domain, that is, if suppose there is a second order differential equation like d square y by dx square plus 10xy 10 into y prime plus 16y is equal to 0. Now, you look at this differential equation. After looking at that, so initial value we have seen that data must be defined at same point. That is, whenever single derivative is there, you can say that y0 is what, or y1 is what, or y1 or y2 etc. But whenever this is for first order ODE, you need only one condition. Second order ODE, you need two conditions. That is y0 is what and y prime of 0 is what, or y of 1 is what, y prime of 1 is what. Again data is defined at 0 or 1 only. So in the first case it is 0, the second case it is 1, but whatever is that, it is defined at a, this is one set, the set of boundary initial conditions are defined at, set of conditions are defined at same location, we call it, it is initial value problem. This is true even if you have third order differential equation, but it must be defined at same point in the form of third order ODE y0, y prime of 0, y double prime of 0, or y1, y prime of 1, y double prime of 1. These are called the initial value problems. Boundary value problems are So that the data must be available at least at 2 points. Why I mentioned at least? When you have third order derivatives, fourth order derivatives, you may be having 4 conditions, but at least two of the conditions must be defined at distinct points. That is y0 if it is defined, second point may be y1, or it is y of a, this must be y of b. 2 different points. Just look at this domain. Of course, you call domain inputs are defined at 0, 1 or a, b. The inputs are defined at 2 distinct values. Therefore, we call it boundary value problems. I'll try to solve one problem. Anyway, the same problem will be solved in the non-homogeneous case also. For time being, I will be focusing on solved problem, that is solve y double prime minus 6y prime plus 8y is equal to 0 with y0 is equal to minus 2, y prime of 0 is equal to 6. So, I have seen already the solution is y is equal to c1 e power 4x plus c2 e power 2x. Roots are 2, 4. So, now at x equal to 0, y value is minus 2. Therefore, minus 2 is equal to c1 e power 4 into 0 plus c2 e power 2 into 0. At y prime at x equal to 0, y prime must be 6, but I have only y value. Therefore, I am applying y prime of x is equal to 4c1 e power 4x plus 2c2 e power 2x. Now, I have y derivative. At x equal to 0, y prime of 0 is 6. Therefore, I am applying 6 is equal to 4c1 e power 0 plus 2c2 e power 0. That implies 4c1 plus 2c2 is equal to 6. Further, you can write it 2c1 plus c2 is equal to 3. You can simplify. And whereas the first condition you can simplify, it is minus c1 plus c2 is equal to minus 2. Now, I can solve for c1 and c2. So, if I subtract 2c1 plus c2 is equal to 3, c1 plus c2 is equal to minus 2. If I subtract, I will be getting minus, so this is plus, and now substitute here c1 5 plus c2 is equal to minus 2, c2 is equal to minus 7. Therefore, your solution is y is equal to c1 is 5 e power 4x minus 7 into e power 2x is the particular solution. This is called the particular solution. Why this is particular solution? You have fixed C1 comma C2 arbitrary constants. Earlier they have freedom. We call it whenever C1, C2 are present in the problem, this is called the general solution. That is, by you can play with those C1 and C2 to give different inputs. You see that all those are solution curves, all those are solutions to the all those curves are solution to the given differential equation. Now you are fixing out of the possible values. C1 may be 0, 1, 2, 3 minus, and C2 is 0, 5, 7, 10, many values are possible. Among all those things, this is you are fixing C1 is this, C2 is this, is called the particular solution. This is possible whenever the initial conditions are available or boundary conditions are available to any specific problem. Suppose you have any boundary conditions, the problem is same, you have to solve that equation with the same procedure. But whenever the given ODE is non-homogeneous, then you should solve the homogeneous first, and the non-homogeneous part. We call it, this solution is called particular integral solution, and we are writing y is equal to y homogeneous plus yp particular integral, ypi. Then you have to fix the arbitrary constants C1 and C2, those are appearing in y homogeneous. You should not solve only after deriving this y homogeneous. You should not substitute those initial or boundary conditions immediately. Whenever non-homogeneous, first solve the complete problem, then you apply these initial or boundary conditions to get the solution. Thanks for watching this video. If you get some knowledge from this video, please like and subscribe the channel for more videos. Thank you.